control voltage. So let us see a very simple circuit of VCO. So if you closely observe this circuit, I have deliberately highlighted this portion because this is external to this circuit. Okay. So understand that suppose this part is not there. Can you identify the remaining circuit? As you see here, there is a positive feedback through two resistances. Then we have a feedback resistor R here and the capacitor which is connected to the inverting terminal. So which is this circuit? Something similar to the Smith trigger. Hope you have identified. Yes? Exactly. So this is a square wave generator. So if we don't have this part, this is simply a square wave generator which you have already studied. So before explaining this slide, I just want to show the simulation so that you will understand the concept of VCO better. So let us move on to the simulation. So here you can see the same circuit. For time being, I am just removing this connection. So let us remove this connection. So remaining circuit, as you see here, there is a feedback, okay, and there is a charging and discharging arrangement for this capacitor. So this is a square wave generator. Capacitor charges through this resistance and discharges also through this resistance, same resistance. And charging and discharging is between UTP and LTP. So how do you find out UTP and LTP here? The power supply is plus 12 and minus 12. Practically, we take the saturation voltage 2 volts below this power supply. So you have saturation plus 10 and minus 10. Both these resistances are equal. That's why when you find out UTP and LTP, it will be R2 divided by R1 plus R2 into saturation voltage. So it will be Vsat by 2. So roughly it is 5 volts and minus 5 volts. So as you see in this simulation, the capacitor will charge between 5 volts and minus 5 volts. So both the waveforms I am going to display. So green waveform will be voltage across capacitor and red will indicate the voltage at the output. As you know, the output switches between plus Vsat and minus Vsat to produce the square wave. So let us simulate. So I will hold just to measure this frequency, and I will put the cursors here corresponding to 1 cycle. Okay. So here you can notice, so the vertical scale is 5 volts per division. So one division, that means this is roughly 5 volts and this is minus 5 volts. So that means capacitor is charging between UTP and LTP, 5 volts and minus 5 volts. And output is between plus Vsat and minus Vsat. Roughly it is 10 volts and minus 10 volts. It is slightly more than this, but this is a perfect square wave. So as you see the time here, it is 2.32 milliseconds. So from that you can find out the frequency. We are not really interested in calculating the frequency. Just understand that this is a normal square wave generator. Now I am just modifying this circuit. I am applying external voltage to the positive loop, that is non-inverting terminal. So let us join this. So what is happening now? The voltage at this non-inverting terminal, to which this capacitor voltage is always getting compared, will nowhere be UTP and LTP, same as UTP and LTP, but now it will be modified because of the external voltage. So if we apply the superposition principle to this loop, we can easily find out the voltage at non-inverting terminal. But let us not worry about this, because we can directly see the effect here. So I have added external voltage, and which is 3 volts. So when UTP appears here, this voltage is also positive and UTP is also positive. So effect will be definitely there is a rise in non-inverting level. So instead of 5 volts, you will get more level for the UTP slightly, and for LTP it will reduce because this is positive and LTP is negative. So let us simulate again and see the change. So as you notice here, now LTP is reduced, or this voltage is reduced. Let us not call it as LTP. The non-inverting voltage to which the capacitor was charging is reduced. So positive side, it is almost same, that is 5 volts, but this is reduced, okay, almost by half. And as a result, you can see the change in the frequency. Let us measure the time period again. So now as you see, it is 1.5. Okay. So by applying external voltage, we have changed the frequency. Let us stop the simulation and now increase this voltage. So instead of 3 volts, now suppose I am applying say 7 volts or 8 volts, and again simulate to see the effect. So notice here the time period was 1.5 milliseconds. So simulate again and let us measure the time period. So now if you see the time period, it is almost 1.633. So time is increased, period is increased. That means frequency is reduced. So did you notice the effect of external voltage that we have applied? So this is very simple circuit that we have modified. Since you are already aware of this concept of Smith trigger, you can just modify the circuit of square wave generator by applying external voltage, and as you see, the output frequency changes as a function of external voltage. So we can call this as control voltage, V control, and we are changing the output frequency of the oscillator. So this is a perfect example of VCO, voltage controlled oscillator. So hope you have understood the concept of voltage controlled oscillator through this simulation. So let us go back to the slides. So this is what just we have seen. So when voltage was given as 4 volts, as you see here, there is the time period as 1.48 millisecond. So for 7 volts, it was 1.55 millisecond. So in BCO, basically, the output frequency is a function of control voltage. So this is very important concept that you should understand. Hope you understood the concept through the simulation.